Good morning, everyone. I'm Dr.M.Sudha, Head and Associate Professor of Mathematics, Sri Sarada College for Women, Autonomous, Salem 16. In this lecture, we are going to see the applications of minimal spanning tree algorithm and shortest root problem. Before coming to these two topics, first let us see the basic notions of network models. What is a network? A network consists of a set of nodes linked by arcs or branches. The notation for describing a network is NA, where N is the set of all nodes and A is the set of arcs. For the given network, see, this is the network given. How many nodes are present? 1, 2, 3, 4, 5. So N is equal to 1, 2, 3, 4, 5. And what is A? A is the collection of all branches. 1, 2, 1, 3, 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, and 4, 5. So N comma A is the given network. What is a directed arc? An arc is said to be directed or oriented if it allows positive flow in one direction and zero flow in the opposite direction. A directed network has all directed arcs. So the above network, that is the network given in example 1, this network, this is a directed network because you can observe that all the arcs are directed. So this is an example for directed network. What is a path? A path is a sequence of distinct arcs that joins two nodes through other nodes regardless of the direction of flow in each arc. So what is a path? It is a sequence of distinct arcs that joins two nodes. Yes, that joins two nodes through other nodes regardless of the direction of flow. So here direction is immaterial. So from the above example, that is from this network, 3 to 5 is a path. 3 to 2, 2 to 5 is a path. See, 3 to 2, 2 to 3 is the direction. That is the directed arc, but I'm taking 3 to 2 and 2 to 5. So regardless of the direction, I'm taking this as a path. So this is an example for a path. So regardless of the direction, you're taking a connection between two nodes through other nodes. That's all. Next, what is a cycle? A path forms a cycle or a loop if it connects a node to itself through other nodes. Node to itself through other nodes. So a path, when a path becomes a cycle or a loop, if it connects a node to itself through other nodes. So it should come back to the starting place. For example, so in the same network, so in this network, from the same network, 2 to 3, 3 to 4, and 4 to 2. So this forms a loop. 2 to 3, 3 to 4, and 4 to 2. This is a loop or a cycle. So starting from 2, it's coming back to 2. So this is a cycle. What is a connected network? A connected network is such that every two distinct nodes are linked by at least one path. Yes. So what is a network? So if in the given network, if every two distinct nodes are linked by at least one path, then you say that the given network is a connected network. Same example 1 is a connected network because all the nodes are connected by at least one path. Next, what is a tree? A tree is a cycle-free connected network. A tree is a cycle-free connected network comprised of a subset of all the nodes. Subset of all the nodes. It is not collection of all the nodes. It's a subset of all the nodes. And it should be a cycle-free connected network. See, in the same example 1, from the network given in same example 1, I take 1 to 2, 2 to 3 as a tree. See this example, 1 to 2, 2 to 3. I'm taking from the from n. N comprises of 5 nodes, 1, 2, 3, 4, 5. So I'm taking the subset 1, 2, 3. So I'm taking a subset of the nodes or subset of n I'm taking. And here, see this path, 1 to 2, 2 to 3. This path doesn't form a cycle. So this is a connected network and it doesn't, and there is no cycle. So it is an example for a tree. This is an example for a tree. 1 to 2, 2 to 3. There is no path from 3 to 1. So there is no cycle here. So this is an example for tree. Next, what is a spanning tree? A spanning tree is a tree that links all the nodes of the network with no cycles. Here also no cycles involved, but it is a tree that links all the nodes of the network. Here all the nodes must be exhibited. See 1 to 2, 2 to 3, 3 to 4, 4 to 5. This is a spanning tree. All the nodes are connected here. Here again no cycles. Next, let us see minimal spanning tree algorithm. This algorithm deals with linking the nodes of the network directly or indirectly using the shortest total length of the connecting branches. Yes. So either directly or indirectly, we are linking the nodes of the network using what? The shortest length. Yes. So this is the minimal spanning tree algorithm. Example, the construction of paved roads that link several towns. An example for this algorithm is the construction of paved roads that link several towns. If you want to link several towns, using road transport, for the construction of roads, we use this algorithm, minimal spanning tree algorithm. The road between two towns may pass through one or more other towns. The most economical design of the road system calls for minimizing the total miles of the paved roads, a result that is achieved by implementing the minimal spanning tree algorithm. Yes. So if you want to frame a most economical design of the road system, that can be achieved by implementing this minimal spanning tree algorithm. What are the steps? Let n is equal to 1, 2, 3, etc. n. So there are n nodes. B, the set of nodes of the network. Define Ck equal to set of nodes that have been permanently connected at iteration k. So the nodes which are permanently connected, they are taken in the collection Ck. Let Ck bar equal be the set of nodes that are yet to be connected permanently after iteration k. So these are the nodes which are yet to be connected. So we have framed Ck and Ck bar from the collection of nodes n. Step O, that is initial step. Set C0 equal to empty and C0 bar equal to n. So initially, all the nodes are to be connected permanently. They are yet to be connected. So they fall in C0 bar. So initially C0 is empty. No nodes are permanently connected. Step 1. Start with any node I in the unconnected set C0 bar and set C1 equal to I, which renders. So if you take the ith node in C1, from C0 bar, you are picking the node I and you are putting in C1. So what happened to C1 bar? It is n minus I. Set k equal to 2. General step k. Select a node J star in the unconnected set Ck minus 1 bar. So you're having CK and CK minus 1 bar. So from the unconnected set CK minus 1 bar, you pick a node J star that yields the shortest arc to a node in the connected set CK minus 1. Yes. Link this J star permanently to CK minus 1 and remove it from CK minus 1 bar. So you are linking this J star node permanently to CK minus 1. So you have to simultaneously remove it from CK minus 1 bar. That is, CK is CK minus 1 plus J star. It is added in CK minus 1 and CK bar is CK minus 1 bar minus J star. It is removed from CK minus 1 bar. So if the set of unconnected nodes CK bar is empty, so proceeding this permanently adding process, finally, if the set of unconnected nodes, if this collection CK bar becomes empty, you can stop the process. Otherwise, set K equal to K plus 1 and repeat the steps until you get CK bar empty. So this is the minimal spanning tree algorithm. Let us see one application of this algorithm. A Midwest TV cable company is in the process of providing cable service to 5 new housing development areas. So a cable company is in the process of providing cable service to 5 new housing development areas. The cable miles are shown on each arc in the following diagram. So the network is given below and the cable miles are shown on each arc. That is the length from one node to another node. Determine the most economical cable network. So this is the question. So we are having 6 nodes and the cable miles are, that is the distance between the 2 nodes are provided on the arc. That is come to the solution, iteration 1. Initially, let us take C1 equal to 1, the first node. And so as a result, C1 bar will be the rest of the nodes, 2, 3, 4, 5, 6. So the distances of the nodes 2, 3, 4, 5 from node 1 are mentioned here, are taken into consideration. And only node 2 is with the shortest distance from node 1. So I am going to permanently add node 2 to C1 and I am going to remove it from C1 bar. So the arc 1 to 2 is shown in dotted lines. Coming to iteration 2. So node 2 is linked to C1. So new C2 is 1 and 2. The nodes 1 and 2. So C2 bar will be 3, 4, 5, 6. Only the nodes 3, 4, 5, 6 are yet to be permanently linked to C2. So observing the linkage. So the nodes 4, 3, 5 are linked with or having link with node 1 and 3 and 4 are having link with node 2. They are having roots. Yes. The nodes 3 and 4 are having roots can be linked from node 2. So observing the distances from node 2 and node 1, node 2, node 5 from node 2, the distance is, the distance of node 5 from node 2 is 3 miles. Is 3 miles. So that is the minimum distance here. So we are going to link permanently node 5 to C2. And we are going to remove it from C2 bar. So in the next iteration, now we have new C3s with 3 nodes, 1, 2, and 5, which are permanently linked. And as a result, C3 bar is 3, 4, 6. Only these 3 nodes are there. So now the minimum distance from node 2 is for the node 4. So node 4 is at the minimum distance from node 4 that is with 4 miles. That is a minimum distance. So I am going to link permanently node 4 with C3 and I'm going to remove it from C3 bar. So in the next iteration, new C4 is the nodes 1, 2, 4, 5 and as a result C4 bar is having only 2 nodes 3 and 6. So here again, the distance of node 6 from node 4 is with the shortest distance 3 miles. So I am going to permanently link node 6 with C4 and I'm going to remove node 6 from C4 bar. So in the next iteration 5, new C5 is then the collection of nodes 1, 2, 4, 5, 6. And so C5 bar is having only one node 3. One node 3. Now the distance of node 3 from node 1 is 5 miles. And also the distance of node 3 from node 4 is also 5 miles. Same distance. So we can choose either the path 1 to 3 or 4 to 3. As a result, in the next iteration, the minimal spanning tree is, so we can take both the options. So the minimal spanning tree could be 1 to 2, 2 to 4, 4 to 3, 2 to 5, 4 to 6, or taking the path 1 to 3, I will get the minimal spanning tree as 1 to 2, 1 to 3, 2 to 5, 2 to 4, 4 to 6. So you can choose either the first one or the second one. Therefore, the minimal cable miles needed to link all the new 5 cities is 16 miles. So this is an example for minimal spanning tree algorithm. Next, let us see shortest route problem. The shortest route problem determines the shortest route between a source and destination in a transportation network. Yes, in a transportation network, what does this shortest problem do? It determines the shortest route between a source and a destination. Other situations can also be represented by the same model. There are several applications of shortest route problem. One of the applications is equipment replacement problem. A rent car is developing a replacement policy for its car fleet for a 4-year planning horizon that starts on January 1, 2001 and terminates at December 31st, 2004. So, a rent car company is developing a replacement policy for a what period? 4-year planning horizon. So the plan actually starts on January 1st, 2001 and it gets terminated at December 31st, 2004. So what does the company do? At the start of each year, a decision is made as to whether a car should be kept in operation or replaced. So at the start of every year, the company is going to analyze as to whether the car should be kept in operation or the car is to be replaced. So a car must be in service for a minimum of 1 year and a maximum of 3 years. So you can have the car in service for a minimum of 1 year and a maximum of 3 years. This is a condition. The following table provides the replacement cost as a function of the year a car is acquired and the number of years in operation. So what is our problem? We have to determine the replacement policy and its total cost. This is the problem. So the following table, this table, it provides the car acquired at the start of 2001, 2002, 2003 and 2004. And these columns provide the replacement cost in dollars for given years in operation. This is for the first year of operation. This is for the second year of operation. This is for the third year of operation. Now the problem can be formulated as a network in which nodes 1 to node 5 represent the start of years 2001 to 2005. So node 1 represent the start of 2001 year, node 2 2002 year, and node 3 year 2003. This is year 2004, and node 5 represent the start of year 2005. So we are framing a network from the given data. The resulting network is this. This is the resulting network. The casts are shown on the arcs, displayed on the arcs. Now the length of each arc equals the replacement cost. See, these are, for example, the length of the arc 1 to 2, it gives the replacement cost $4,000. And similarly, other arcs. The solution of the problem is equivalent to finding the shortest route between nodes 1 to 5. Yes. So we are providing solution for this replacement problem by applying the shortest route problem technique. That is, we are finding the shortest route between node 1 to node 5. The total cost of the replacement policy is calculated as below. So if you take this path, the straight path, 1 to 2, 2 to 3, 3 to 4, 4 to 5, if you sum up these costs on the arcs, so we are getting $13,000. Similarly, if you take the next route, 1 to 2, 1 to 2, 2 to 4, and 4 to 5, if you sum up the cost, you are getting $15,000. Sorry, $15,100. Similarly, in the next part, 1 to 3, 3 to 4, 4 to 5, the total cost is $15,100. If you take this path, that is 1 to 3, 3 to 5, where is it? See, this is 1 to 3 and 3 to 5. The cost is $12,500. So if you take the next path, 1 to 4, 4 to 5, the cost is $16,900. In the last path, 1 to 2, 2 to 5, the cost is $12,700. So if you observe all these total costs, which one is minimum? $12,500 is minimum. So it corresponds to which path? 1, 2, 3, 3 to 5. Therefore, we conclude the shortest route is 1 to 3, 3 to 5. So what is our solution to the replacement problem? So the solution means that a car acquired at the start of node 1 means at the start of 2001 year must be replaced after 2 years. That is at the start of 2003. Yes. That is, a car acquired at the start of 2001 must be replaced after 2 years. That is at the start of 2003. The replaced car will then be kept in service because we are having 4-year period. So it should be kept in service until the end of year 2004. Until the end of the year 2004. See, the car acquired at 2000, start of year 2001. It should be replaced at the start of year 2003 and it should be kept for 2 years operation and it should be replaced. See, this is the start of year 2004. So it could be in service till the end of year 2004. That is at the start of the year 2005. So the total cost of this replacement policy is 1 to 3, the cost is $5,400. 3 to 5, the cost is $7,100. So the sum is $12,500. So the replacement, this is the replacement policy and the total cost of the replacement policy is $12,500. Thank you, friends.